In this video, I'm going to introduce some concepts of a branch of math called trigonometry that is everything to do about right triangles and how we can use triangles to solve problems. In this part one, I'm going to define some important terms and some things we will use and see in trigonometry. And in the following videos, we'll use those definitions to set up and solve some problems. The key feature or key thing we're going to use and study in this branch of math called trigonometry is something called the unit circle. And a unit circle is a circle with unit radius, meaning a radius of 1. And I have a unit circle drawn here. It's centered at the origin, and the distance from the center to the edge is 1 unit. We're going to define we'd like to know some things about the unit circle. In particular, we'd love to know how to find points that are on the circle. And we define the coordinates of any point on a unit circle in this way. If we have a point that's on the unit circle, and you can draw a radius out to it. First of all, we know this radius is 1. And we define the coordinates of this point, of any point that's on the unit circle, in the following way. We say that the y-coordinate is this thing called the sine of this angle that's being made. We say the angle being made, we'll mark the angle here. This angle, whatever it is between the x-axis and the radius that we made, the most common symbol is this one. It's a little circle with a line through it. This is the Greek letter theta. And this is the common symbol. This is the Greek letter used for angles. And you'll see this in every math class you take from here to the last math class you take. It's the Greek letter used for angles. We say that in relation to whatever this angle is, that the y-coordinate is what's called the sine, in abbreviated your calculator abbreviates sin of theta. And that'll be the y-coordinate. The x-coordinate is called the cosine, or cos for short. We say cosine of an angle, or the sine of an angle. So what does this tell us more? Well, let's see. The x-coordinate is how far you would walk in the x direction from the origin till you get right underneath of the point you're after. So you could draw in, say, a distance. And this distance from the origin to right underneath this point would be a length of cosine of whatever this angle is. And then if you do the same thing, the y-coordinate tells you how far up to walk. So if I get right under this point and I walk straight up and I hit this point, and if I was better at drawing on my computer, it'd be a straight line. This would be, we'd call whatever this distance is called the sine of this angle. And note that if the angle is shallower, it's not as big, then to get underneath this point would travel kind of maybe farther along, so this cosine gets bigger, and the sine, this point is not as high up, so the sine gets smaller. And vice versa. If the angle is really steep, like close to 90 degrees or so, then we don't have to walk very far out, so cosine is small, but we walk pretty far up, so sine gets big. And if you're right at 0, then the x-coordinate would be 1, so the cosine of 0 is 1. And the sine of 0 degrees, of not rotating at all, would be 0. So just some features. What does this do? Well, if you notice, it's badly drawn, but notice here by this construction, I've made a right triangle with hypotenuse of 1. One of the legs is cosine, and one of the other legs is sine. And we're going to use that to try to help us kind of generalize this for any right triangle. So what if we have a triangle that's not necessarily from the unit circle? Maybe this triangle has annual radius any old hypotenuse. This is a right triangle though. It could have any old length. I don't know what the length of the hypotenuse is, but I'm just going to call it the hypotenuse. What I'd like to do now is I'm going to choose one of these angles to be the angle I'm considering. It doesn't matter which. I'm going to choose just for convenience this one because we're going to do a little transformation here in a second. But maybe I'll call this angle here will be the angle from the perspective I'm going to look. From this angle's perspective, I want to identify, I want to give names to these other two legs. And this is how I'm going to identify them. From this angle's perspective, I'm going to find the angle that's opposite or across from the side that's across from this angle. So the side that's opposite of this, I'm going to call this the opposite leg. Now note if I was looking from this angle's perspective, the opposite leg would be down here on the bottom. And then also I'm going to identify, I'm going to label this one in blue like I did before. And then the other leg, note the leg of this right triangle, not the hypotenuse, but the other leg, I'm going to call the leg that's touching this angle here, or is adjacent to it. So I'm going to call this the adjacent leg. So I've named the sides of this, and I'd like to try to see how can I use what I just saw to maybe set up and do something more with. What I'm going to do is I'm going to take this triangle and I'm going to translate it so that the corner where this theta is right on the origin of a circle. If I've chose this angle up top, then I would rotate this triangle, maybe reflect it, do some transformations that don't change the size or shape, some isometries, and move it so that this corner was on the origin and one of the legs is right on the x-axis. Since I chose this angle, it's going to be easy. And to do that, I'm just going to, on my computer, I'm just going to drag it to try to make this a little more visual. But I'm going to drag this triangle. I'm going to translate it and rotate it if I needed to, and I would move it so that this triangle is right on the origin. Something to notice is that now what I have is I've got my original triangle with the hypotenuse. I've got my opposite leg is over here. The adjacent leg to my angle is here. But also note that that this triangle intersects a circle right here. And if I were to draw an altitude or drop a line that's perpendicular straight down, I'd make another smaller triangle. This point that's right on it, on the circle, if this angle is theta, like we said before, this has coordinates. And as we defined before, this coordinates of cosine of this angle and sine of this angle. And the radius of this unit circle is 1. So what I end up getting is actually two triangles that are both right triangles, so they both have a 90-degree angle, and they both share this angle theta. Therefore, these triangles are similar, which means I should be able to set up some proportions based on the side lengths. And I'm going to redraw these two triangles here. So I've got the little small triangle of angle theta, radius 1. As we said, the height, or this leg here, excuse me, this leg is sine. This other leg that goes along with the x-coordinate is cosine. And the radius is 1. In my original triangle is the adjacent leg, the opposite leg, and the hypotenuse. And they both have angle theta. From this, we can set up some ratios, using, or some proportions, to try to make sense of what some of these symbols would mean. And here's a couple of clever ways. The first ratio I'm going to say is the sine of our triangle. I'm going to compare the blue side to the black side. So I think one way to write the sine, or define sine in terms of any old triangle, is that we say the sine of an angle over 1, sine to 1, in the other triangle would be opposite compared to hypotenuse. So sine over 1, or sine of an angle, is the opposite leg divided by the hypotenuse, opposite over hypotenuse. Cosine, if we do something similar with cosine, cosine over 1 should be the same as red over black, or adjacent over hypotenuse. So now the adjacent leg. Over the hypotenuse. So what this tells me is that if I have any old right triangle, I can actually calculate. I know something about, if I know something about the angle and one of the sides, or if I know both sides, I can know something about the angle. I can figure out some values based on this. These sines and cosines, these coordinates along a unit circle, are very well known. In your graphing calculator, as we're going to see in future videos, is really good at knowing how to calculate these values. So if you know the angle, we can figure out what the sine of this angle is, or what the cosine of the angle is. These are decimals, somewhere anywhere from 0 all the way to 1. There's one other important thing feature of this we see. It's called the tangent of an angle. The tangent is what geometrically we say is, if you look at a radius of a unit circle, we say the tangent is the slope of that radius. So again, depending on how big the angle is, the slope, we'll say the slope of this radius is its tangent. So note the slope could be 0 if it's horizontal. The slope could be positive. It could be very, very positive if the point is really close to 0, 1. Or the slope could be very negative, because we start here and could go down anywhere. So this tangent kind of means that. So I'm going to write down that the tangent, we say that tangent of an angle is the slope of a radius of the unit circle. And much like sine and cosine, we can define this in terms of any old right triangle. So note, even if we have a similar triangle, the slope of, we say the slope of this triangle, that would be the rise over run of the unit circle is going to be in the same proportion as the rise over run in any big triangle. And again, we say the slope, which is rise over run. And this is, we say, is the tangent of an angle. Say tangent of theta. Note that in my triangle, we say that usually abbreviate TAN for tangent. The tangent of my angle should be the rise over run. So if we think of starting at a point, how far do you go up? Well, you go up this amount, which is, well, the opposite side. And how far do you go to the right or left? That would be the length of this adjacent leg. So these three what are called trigonometric functions, or trig functions, are things we're going to, and these definitions are things we're going to use to solve some problems, and primarily using a graphing calculator.